All right, so 7.2 is on rational exponents, and I mentioned this a little bit in your 7.1 video. I have similar directions as in the last video. The only difference is that I added in how to do it as an exponent, a rational exponent, since we're dealing with rational exponents here. So you can also put it as a fraction, a rational exponent, by doing the caret. So it raises it to that power, and the power being 1/3 power, and we'll talk about why it's 1/3 in just a moment. You just need to make sure to put it in parentheses. Otherwise, what it does is it does 8 to the first power, and then it would divide that by 3. So you'd end up with 8/3 rather than 8 to the 1/3. So here is the rule that I mentioned in the last video as well, that you can have m divided by n when you're simplifying your rational expressions, your radical expressions here. You can change it and think of it as a rational exponent. And so you can do it when it's underneath like this or outside. The idea is that it's the exponent divided by your index value. And the index value, again, is the nth root, if it's a square root or a cube root or a fifth root, etc. And again, the square root is just the one that doesn't have a number in there. It's an implied 2 because we're just used to this symbol meaning square root. So it's an implied 2. And just like we mentioned in 7.1, we cannot take a square root of a negative in the real number system. And so it just mentions that this rule only holds true in all cases when what's in here is positive. All right, so when the exponent is an invisible 1, so x here means x to the first, then you end up with 1/n. So here we go. We can break this up into the cube root of x to the 6th times the cube root of m to the 15th. So then 6 divided by 3 is 2. I'll do that in a second. And then m, it's going to be 15 divided by 3, which is 5. So this ends up being x squared m to the 5th. Assuming that we have positives here. And if we raise anything to the 6th power, it would be positive. Here, it could be a negative when you raise it to the 15th, but we're going to assume that the variables are positive. It will often say if you're not assuming, normally we just assume they're positive unless otherwise told. Otherwise. Okay, this next one, I am going to simplify it. There's 2 ways to do it. One is to try to use your calculator and do 8 to the 2 divided by 3 in parentheses and see if you get a nice value. So let's see, 8 to the parentheses 2 divided by 3, end your parenthesis. Oops, I was trying to enter, and enter 4. The other option is to rewrite it as a radical, and so this would be 8 to the 2/3. So it's kind of this counterclockwise motion, and I mentioned this counterclockwise motion also because it'll come up when we deal with logarithms. 2/3. And so now when I do this, I could either take the cube root of 8 times 8, 64, or I could take the cube root of 8 and raise that to the 2nd power. So cube root of 64 ends up being 4. The cube root of 8 would be 2, and then if I square that, I get 4. So no matter what method I use, I'll get 4. And when I do this, I can write a factor tree for 8 and have 3 2s, so then 2 and then square it. for this, I could do a factor tree for 64, and I would have 4 3s. Actually, I would have 3 4s. I would really have 6 2s, but I can group them. So we'll see that later, how to deal with the factor trees. Number 3, because it's a negative, just like we have with the rules of exponent, which I've posted here as well as reference, it's the same. We can do 1 over 9 to then the positive 1/2. We can take the reciprocal. So you could type this in your calculator and you would get 3. However, we're going to move to places or situations where we don't have a nice number, like a perfect square root. And we're also going to have times where we have variables. So I want a method that works in all cases. So this would be 9 to the 1/2 power. So 9 to the first, right? 9, and then square root, so 1/2 power. And the square root of 9 is 3. Because 3 times itself is 9. So when you have a fraction with a negative exponent, we did this before when we were doing our exponent properties, we can take the fraction part, flip it over, take the reciprocal, and make that the positive exponent. Or you could do 1 over and make it a positive exponent, take the reciprocal, but then you end up with a complex fraction. So I can take the 3/2 power of both my numerator and denominator, which is the same thing as saying 9 to the 3/2 and 25 to the 3/2. And again, I can either raise this to the third and then take the square root, or I can take the square root and then raise that to the third. So if I take the square root of 9, that's 3, and then I can cube it. Here I can take the square root of 25, it's 5, and cube it. So if it's a nice number, I do that part first, so I make the number smaller before then making them bigger. If it doesn't go in nicely, then you might consider doing the exponent first, and then seeing if you can take the root of that. So 3 to the third is 27, and 5 to the third is 125. Because cubing and cube rooting would undo each other. There should be that relationship that we saw earlier with 5 and 125. So again, 1 over 8 to the positive 2/3 plus this would be 1 over 100 to the 1/2. We did 8 to the 2/3 earlier. Right here, it's 4. So it'd be 1/4 plus, this is like saying the square root. A half power is the same as square root because it's 1/2 then. So that's 10. Square root of 100 is 10 because 10 times 10 is 100. So we end up with 1 over 10. We would need a common denominator. The lowest common denominator between 4 and 10 is 20. Multiply by 5 over 5, so you're not changing the value of 1/4, but you're getting a common denominator of 20. Same here, 2 over 2. So we end up with 5 over 20 plus 2 over 20, which is 7 over 20. When you have a common denominator, you can add your fractions, you add the numerators, and you keep the common denominator. You'd reduce that if possible. The next couple are rational exponent arithmetic problems. It's basically the same rules as we had when it was integers earlier in this course in chapter 1, except that we're just dealing with fractions, but those same rules apply. It's a little bit harder to, draw out 2/3 or 5/3 of these things. But the same rule applies. So when we have the same base, we ended up, when we're multiplying with the same base, adding the exponents. For example, if I had x squared, x to the third, we ended up having x to the fifth because it was x times x, that's x squared, times x times x times x to the third. We have 5 x's multiplied here. So again, we add when we have the same base. So I'm going to do 2/3 plus 5/3. So I have a common denominator of 3, so I can go ahead and add my numerator, 7, and keep my common denominator. You can leave it as 7/3 since the original problem was written with fractional exponents. I will mention to you, though, that this is equivalent to x to the 7/3, which, because 7 divided by 3, we would have 2 groups going out completely, and then you'd have 1 left over. It could be written like this, and we'll talk more about those cases later. All right, next one with division, you would subtract, so 4/5 minus 1/5, that would be 3/5. Or you could write it as the 5th root of m to the 3rd. The 3 can either go underneath the root symbol or outside of it. Number 8 here, power to a power, that's when you would multiply. So you're going to have 1/2 times 3/4. For the y, you'd have 3/5 times 3/4. For the z, you'd have 2/3 times 3/4. So this is a great review of just rules of exponents and great review of how to work with fractions. So this would be 3/8, because 2 times 4 is 8. 9/20. And 6/12, which is 1/2. You could also cross cancel those and then reduce those and get the 1/2 that way. But we do want them in reduced form. Again, since it was given with fractional exponents, we can leave our answer with rational exponents. We don't have to write it as a radical. If we wrote it as a radical, we'd have to get a common denominator, because remember, the index was that denominator. So we need to get these to have a common denominator to write it as a radical. Number 9 here, a power to a power, you would multiply. You have, oh, that's the same as saying -8, so I'll just go ahead and write -8. When you have a negative exponent, you can make it positive, which is how you simplify. You always want to have positive exponents by bringing the factor that has a negative exponent to the opposite position, numerator to the denominator or denominator to numerator. That's taking the reciprocal. So when you have a negative exponent, you want to take the reciprocal to make it a positive exponent. So if I bring it down there, then that invisible 1, the coefficient, is still there because it's 1 times. So it's just the factor that had the negative exponent that we change the position on. In other words, I need to have something there. I can't have a blank. And it went in as a reciprocal, so it becomes 1. Number 10 is kind of an interesting example. Just to reiterate what this all means, this is a to the 1/2, and then it's to the 1/3. And a power to a power, you multiply, so 1/6, which can be written as the 6th root of a to the invisible 1 here. Which in this case, it's written as a radical, so this would be the more appropriate response, although it's equivalent to that. So 1/6, and again, you don't need the 1, I just was putting in there to show it. Lastly, this one is a cube root. So cube root of 125 was 5. We've seen that a couple times now. We're going to have r to the 2/3, and then m to the 6/3. You could have written 125. I'll go ahead and do that. 125 to the invisible 1/3 also. But that's a cube root, so that was 5. R to the 2/3, and then m to the 2nd power. and they had it as a radical, and they wanted it as an exponential. So we did do one property that I did kind of 2 steps in one. I just wanted to note, because this rule here of a fraction to a negative, it's applying this idea of the fractions and how to deal with them. Oops, sorry, the fractions and how to deal with it when it's power number 5. And it's also incorporating the idea of a negative exponent, which is here number 4. So if you put 4 and 5 together, you get this shortcut. When you have a negative exponent with a fraction, you can do the reciprocal, so b over a, and make it a positive exponent. That way you don't end up with complex fractions, and it's just an easier problem that way. So that is it for 7.2. And again, the rules for how to do all the different roots are in the last video. I went through and showed how to use the calculator for all these things. And I did a little bit at the beginning class on that, the case where you're doing it as a rational exponent.